Okay, I'm not even going to ask you. You probably didn't do these examples and you just hit play on the next video in order to cheat from me. And again, if so, then I guess that's okay. I would never know. But here we're going to answer part A together. And I told you if you were going to do them, if you were uncomfortable with stereoisomers, just leave it off. And then just predict the product. You can do that. I mean, you don't have to worry about the solid and dashed wedges, because you can still predict products that go on. You know, what happens to the OH group, what gets replaced with the OH group, all of that you can help determine. But the stereochemistry might have given you a problem a little bit. So I want to go back to, oh gosh, look at all of those notes that we took in the last video. Whoa. All right, so let's start with A. We've got this ring structure, and I'm not going to worry about stereochemistry, not yet. And we are reacting this with P, Br3, and then pyridine, if I can spell it the right way. And then in step 2, we're going to react this with OCH3. And here is the OH group. Okay, so let's not worry about stereochemistry. Let's just kind of figure out what kind of products formed. Pretty easy. Here we go. There's my ring. There's my methyl group. Here is my OH group. Okay, so what happens in this reaction? PBr3 and pyridine. So it targets my OH. This prevents rearrangement. It's one of those 3 that prevents rearrangement. That's why we use it. So no rearrangement's going to happen. And that is where my bromine is going to go on. And then after my bromine goes on there, look at step number 2. I'm going to replace that with a prettier person. And that bromine is then going to be kicked off, and OCH3 will go on instead. That's how we do that. That's kind of the overall goal of this lecture. Now, with that comes a lot of details. And part of these details is this whole stereochemistry branch of stuff that we're going to have to worry with sometimes. All right, so here we go. There's our solid wedge, and there's our dashed wedge. So my solid wedge is here, and my dashed wedge is there. And I'm just going to start all over again. Okay? So the way that we do this, the first step, my bromine gets added on. And it adds on in a substitution reaction. Okay, the OH group has to leave, and my bromine goes on. But when that happens, my bromine snuck through the back door. So what was a dashed wedge now turns into a solid wedge. So there's the first step. In the second step, I bring this nucleophile in, and my bromine leaves, and it gets replaced with an OCH3 group. But in order for that to happen, that had to get substituted, didn't it? The bromine had to leave, and my OH had to sneak through the back door. So we go back to the dashed wedge at that point. And this is what we've talked about in the last video. I said whenever we use PBr3 or PCl3, that kind of material, folks, you get the same stereochemistry than what you started with. Same thing. If it was a dashed wedge, it's going to be a dashed wedge. If it's a solid wedge, it's going to be a solid wedge. There's no difference in the stereochemistry because these things happen in 2 full-blown substitution reactions, each one requiring a Walden inversion. So, first step, dash goes to solid. In the second step, solid goes back to dashed. And that's why we end up with the same thing. All right, so there's part A. Now, let's take a look at part B. Part B gave us the same molecule, but this time, still a solid wedge up here, right? And still a dashed wedge down there. But I told you that we're just going to ignore this for now. We'll just look at the product, and that's it. And we're going to react this with HBr and a little bit of heat. Okay, no big deal. So here's my ring, and this is where we start off. So the purpose of the HBr is that the H will go on, bam, give it a black eye, make it ugly, and this OH group decides to leave. This is a secondary carbon, so that secondary carbon is going to form a full-blown carbocation. So that thing is going to be positive. Will it shift? You know, that's the problem with HBRs and HCl's. These acids allow for carbocation rearrangement. That's how this one's different from part 1. So the answer is yes, it does shift, and it will shift up there because this is a tertiary spot, and where it was is a secondary spot. So it does move, and this is going to be the incoming group now. This is where it's going to be as far as waiting for the bromine to come back in. So here, my carbocation, that's my bond form, and my bromine is going to come on and attach in that position. Now, what about stereochemistry? Well, I'm going to get a mixture. Because of that, I'm just not even going to draw it. You know, when that carbocation shifts, it goes to that carbon. That carbon is kind of like a chiral carbon. There's 4 different groups pretty much that's there. So with that said, sometimes the bromine goes front and sometimes the bromine goes backward, and it's like a 50-50 split. So we just kind of leave it off. We don't even draw the stereochemistry that's associated with it because it's not a direct route of one form over the other. So I'm going to get a racemic mixture. That's what that is called. So sometimes solid, sometimes dashed, and we just leave it off just because we get both. All right, so now let's take a look at C. C was a ring structure. There we go. I see an OH group and a methyl group. And in this case, we're going to add on SOCl2 with some pyridine. And then we're going to add on my OCH3 group. Okay, so let's talk about this without stereochemistry first. I'm going to redraw my reagent. There's my OH, there's my methyl. So what happens in the first step here is that my SOCl2 will basically go on to this alcohol group, and that alcohol group is going to turn into like this SOCl group, right? And then the chlorine goes on from that SOCl2 group. I mean, that's kind of what happens there. That chlorine kicks that back off, and we have just now halogenated that compound. So there's the first step. My SOCl2 group reacts with the OH, that leaves, and my Cl goes on. There's my first substitution. Then in the next one, that chlorine now is going to leave because it's an ugly group, and that is going to get replaced by my OCH3 group. So the whole purpose of the SOCl2 is to put a halogen on it, just like all before. So now let's take a look at stereochemistry. In the beginning of the problem, it said that this wedge up here, this was a solid wedge. So it's still going to stay a solid wedge. This one down here is going to be a dashed wedge. All right, so in my product, that stays solid. That's what we just said. Down here, though, we're going to go back to the original. We're going to talk about this again. And I'm going to start off with my dashed wedge. So there we are. So this was an OH group, right? So when the SOCl2 came in, well, that activated the OH group, that left, and what we have here is a chlorine that came in and substituted for that compound. When that happened, that chlorine had to come in an SN2 reaction. It had to come through the back door. So that is a secondary carbon. No rearrangement happens with these thionyls. So that turns into a solid wedge. Now, in the next step, that chlorine is an ugly group. It's got to leave. Well, the OCH3 is a prettier group, and that's what the carbon wants. So again, another Walden inversion has to happen. That piece sneaks through the back door, and that replaces the chlorine with the OCH3 group. But because it snuck through the back door, why do I keep saying that? The back door, that wedge goes back to be a dashed wedge. So just like with PBr3, PCl3, the thionyl chlorides do the same thing. What you start off with stereochemistry-wise, you end up with stereochemistry-wise. There's no overall flip of what happens with the stereochemistry. All right, now for Part D. Part D gave me the same thing all over again. CH3 there, OH here. I'm not going to worry with stereochemistry yet. And then on this arrow, just to save some space, they wrote, first, you're going to react this with tosyl chloride and pyridine. Doesn't that make you sound fancy when you say tosyl chloride? And then OCH3 group. All right, so over here, I'm going to draw the starting reagent. This is where we started. And now what we'll do is we'll just look at product, hard product, that's it, no stereochemistry. The O group turns into this O with the tosyl group. So notice that oxygen really didn't get replaced. This is part of that kind of intermediate stage of making this product. So no backdoor flip happened here. No Walden inversion happened. That oxygen is still an oxygen. It's still in the spot, but tosyl now has just made its way in instead of that hydrogen. So nothing flips yet. Now this is a very good leaving group, and that leaving group is pretty ugly. So carbon kicks it to the curb, and the OCH3 group goes on in its place. So overall, this molecule has an alcohol group. This prevents rearrangement. That OH group leaves, and the OCH3 goes on in its place. That's kind of what happens here with all of these. Now let's talk about stereochemistry. All right, up here at the top was a solid wedge. That never got touched, so it's still going to be a solid wedge up here. Down here below, this was a dashed wedge. So notice in the very first step, I said, okay, what happens with the tosyl is that hydrogen gets removed pretty much, and that tosyl goes on with that oxygen. So no substitution really happened here. Nothing got substituted. The O was there, and the O is still there. So nothing had to flip. So it's still a dashed wedge at this point. Now, this is where the flip happens, because now that is a good leaving group. It's ugly. Carbon's going to cheat. Carbon's going to sneak the methoxide through the back door, and what we will end up with at that point in time is a removal of that group. We add on the OCH3 group that had to sneak through the back door. So we do get a flip in the stereochemistry because of that. So both of these now are pointed toward us, not one toward and one away. So that's how we answer those questions. And we're keeping stereochemistry in mind as well. So again, we did one version without stereochemistry involved, and then we did another version where stereochemistry was pretty important. All right, let's take a look at another example. This one, show how 1-propanol can be converted into the following by means of a sulfonate ester. Okay, so here is just really a recap, a review of the sulfonate esters. I mean, that's all that we're doing. I'll show you how easy this is. 1-propanol, so prop is 3, so CH3, CH2, CH2OH, right? We need to add a sulfonate ester. So we know good and well the most common sulfonate ester here is my tosyl chloride. And that's really the one to go to almost every single time. So tosyl chloride needs a little bit of pyridine for the solvent. And when tosyl chloride goes on, folks, it's going to target that OH group, and that OH group is going to turn into a very good leaving group. So what do you want to replace that with? Well, if you look up here, 1, 2, 3 carbons. There's the propanol piece. So what I want to replace that OH group with is that piece right there, SCH2CH3. So in round 1, I'll do tosyl chloride and pyridine, and then my second step, I will simply add on sulfur with my CH2, and my CH3 group. That's as difficult as those problems need to be. Now, if I take a look at part B, let's look at that one. Part B says the same thing, starting with propanol. Okay, so CH3, CH2, CH2OH, and I need to add on a sulfonate ester. Well, the preferred sulfonate ester here is tosyl chloride with a little bit of pyridine. So what do we want to do in round 2? Well, let's look at what we have to add. So 1, 2, 3. There's the 3 carbons from the propanol, and it looks like I'm going to have to add on this piece here. I want my OH group off. That's the purpose of the tosyl chloride. And I want to replace that with that group. Okay, not a problem. I'll do an O, CH2, CH, CH3, and CH3 that goes down. That's it. That's all that you got to do in order to answer question A and question B on how to make these products from an alcohol. Folks, this really would have happened kind of the same way if I used PBr3, PCl3, SOCl2, all of those, wherever that OH group would be, would target that OH group and replace it with a nucleophile that I want to add on to the compound. And that is how we answer those questions in every single case. This would not work with HCl and HBr. And the reason is because rearrangement can take place. And that rearrangement, very important. You got to watch out for it. And this could rearrange and not place the nucleophiles where you want them to go. You just got to be really careful with that kind of stuff, all right? I'm not saying that it would happen every single time especially, but it could. And that's something that you always want to watch out with those acids. All right, so that's where I'm going to stop this video. And the reason is because the next lecture topic that we are going to be focused on is yet again alcohol reactions. But these alcohol reactions are now going to be in the world of elimination. So we've done substitution after substitution really with the first round of alcohols, right? We added HCl's in order to replace the halogens a little bit later. We added the PBr3s, the PCl3s in order to replace the halogens a little bit later. The thionyl chlorides, the sulfonate esters in order to replace those leaving groups a little bit later. So all of these were substitution related reactions, which is why I gave you a review of substitution in the lecture module folders, but there were no assignments assigned to it because these are things that need to go along with Chem 251, not here. So if you did not get that or you were rusty on it, go back and review those. I think that would make this process much easier. Now we're going to turn focus to elimination, which is why I gave that folder to you available as well with no assignments, just in case you needed a little review or you were rusty on the elimination part of the procedures. So in this next lecture series, or in the next coming videos, probably I would say a handful of videos, we're going to look at elimination reactions of alcohols. Very important. So again, go back, watch those older elimination videos from Chem 251 if you need to, and then maybe pick up from here and then work from the alcohol reactions at that point. I think it will make this process way easier for you if you do that. So I'll be here when you come back, and we'll talk about eliminations of the alcohol group, which I think you're going to find out is not as difficult as it sounds. You eliminate it. That's really all that you got to do. How hard can it be? You'll find out when you come back.